The following was made as a television videotape. Its purpose is to provide orientation for those teaching the CHEM Study course.
One of the most significant differences between the CHEM study and traditional treatment of a familiar topic is the picturization of the atom. Instead of using the familiar planetary model of the atom, in the CHEM study course we use a quantum mechanical view. Now I'm sure that you'll want to know why such an important change was required. Obviously, the planetary model is the simpler of the two. It has two crushing defects, however. It has never been successful in giving a quantitative explanation of any atom with more than one electron, even the helium atom. More important even to a chemistry class is the fact that it has never provided any basis for understanding the existence of chemical bonds. Now, the quantum mechanical view is admittedly more abstract. Mathematically, it's more difficult to convey, but it has the two advantages that it has provided a mathematical quantitative understanding of many electron atoms, and where the mathematics could be solved, they are always found to be consistent with chemical phenomena. Consequently, quantum mechanics and the quantum mechanical view of the atom give us a chance of understanding chemistry. Now, we're going to show you today the film, The Hydrogen Atom, as viewed in quantum mechanics, and I wanted to tell you before you see the film that there are two versions. You'll be seeing the longer version, and there is, in addition, a shorter version that includes about the first two-thirds of this film. And I'm sure that you'll be able to decide which of these two versions is more appropriate to your own discussion and classroom use. I want to use the rest of the time today to talk some about hydrogen atom orbitals as viewed in quantum mechanics in agreement with this film. But before I do this, let me tell you about next week's film. Next week you'll see a 30-minute film that was made for teacher education concerned with the mathematical background of quantum mechanics. Its purpose is to give you some feeling of confidence of the mathematical soundness of quantum mechanics, some depth beyond that which you'll discuss in the classroom. Now, let me go back to the hydrogen atom orbital as viewed in quantum mechanics and review some of the ideas you've just heard. In the first place, you see that the trajectory of the electron is no longer an important factor, and indeed quantum mechanics is not able to answer trajectory questions. Instead, we find that the electron distribution is discussed in terms of probability. We find that in discussing the electron distribution near the nucleus, that we have to talk in terms of probability, and that this probability has maximum density near the nucleus and extends out to infinity. At higher energies, as for instance in the 2s orbital, the electron distribution is again discussed in terms of probability, but the higher energy corresponds to a high probability of finding the electron a larger distance from the nucleus. Also, at this higher energy, it's possible to have spatial distributions in which there are nodal planes, that is, planes in which the probability of finding the electron is vanishingly small. And in the case of the 2s orbital, there's a spherically symmetric nodal plane. In the case of the 2p orbital, there is a plane of symmetry here. And then we find in still higher energies, as in the case of the d orbitals, more complicated angular distributions. These angular distributions are characterized by the quantum number n that was given such emphasis in the film. And the quantum number n can be 1, 2, 3, any integer value. And this quantum number n is sufficient to determine the energy of the electron. And in fact, the energy of the electron, referred to the separated electron and proton, is minus 313.6 times z squared, the nuclear charge, divided by n squared, the principal quantum number. Now you understand that the one electron problem does not apply only to the hydrogen atom. It applies to any nucleus with a single electron. And consequently, we're interested in the energy for still higher nuclear charge, Z. But the important point is that although there is only one state for the n equal 1, there are several states with the same energy for n equal 2, still more for n equal to 3, and these states have energies, even though there are many, which depend only on the principal quantum number. As the principal quantum number gets higher, the size of the orbital expands, and the difference between these various possible states has to do with the spatial distribution. This will be the 1s state, the 2s, the 3s. These will be the 2p states, 3p, and 3d. Now it's possible to discuss the many electron atom in terms of this simple picture that we have here, the hydrogen atom energy levels. And that's why it's so important to understand the hydrogen atom energy levels. The many electron atom can be discussed in these familiar terms if we just add one idea, and that is the idea that as we place electrons into the lower energy levels, those electrons screen electrons in higher energy levels because the higher ones are further away. This idea of screening by inner electrons permits us to discuss the outermost electrons, those in the higher orbitals, in terms of this one electron formula, provided we put in an effective charge, the charge felt by the outermost valence electron in view of the fact that it sees the nucleus through a screen of the inner electrons. With that one new idea, we can talk about the many electron atom in terms of this simple picture. Now, this, however, adds one new facet to the discussion of the atom, now the many electron atom, and that is that different types of spatial distributions, as represented by the S, the P, the D, feel a different extent of screening by the inner electrons, and you can see why. The 2s electron, part of the time, is very, very close to the nucleus. The p electron, on the other hand, the 2p electron, which for the hydrogen atom has exactly the same energy, never gets very close to the nucleus. The result is that inner electrons, the 1s electrons, are more effective in screening a 2p electron than they are for screening the 2s. The result then is that these levels are no longer exactly identical in energy. Instead, there is a tilting. The 2p levels are slightly higher in energy than the 2s. This effect is even more extreme when we get to the 3s, 3p, 3d. The 3d electrons are so rarely near the nucleus because of this complicated spatial distribution that this 3d level is cast very high in energy. The result of this, then, is that the 3d electrons are brought up into approximately the same energy as the next higher principal quantum number. And as far as this simple description of the energy is concerned, we see that the picture has become just slightly more complicated in that now, in addition to n determining the energy, there is some influence by whether it's an S, a P, or a D, the spatial distribution. With this understanding, we are then able to construct the entire periodic table. with the familiar Pauli principle that each orbital can contain only 2 electrons. The one electron picture with the idea of screening and the fact that different types of orbitals give slightly different extents of screening.
This is a CHEM Study film, a production of the Chemical Education Material Study. Here is the filament in a tungsten lamp. As the filament is heated, it emits energy in the form of light. Although the light appears white to our eyes, when we pass the light through a prism, it is separated into a continuous spectrum of colors. This continuous spectrum shows that a tungsten lamp emits photons of all energies. This is a gas discharge tube containing hydrogen. The light emitted by this tube is due to hydrogen atoms. Let's look at the spectrum of this light source. This time we see a line spectrum. Each line corresponds to just one possible energy change in a hydrogen atom. We see that very few energy changes occur in hydrogen atoms in contrast to the tungsten filament. Accurate frequency measurements tell us the energy changes and lead us to the hydrogen atom energy level diagram. But how can we explain the fact that the energy of a hydrogen atom has only these certain values? We begin with a simple picture of the hydrogen atom. At any given instant, the electron is separated from the proton by some distance, r. The electron and the nucleus have opposite electric charges, so they attract each other. This attraction gives the atom a certain amount of potential energy. The amount depends on the distance, r. The electron is in motion, and so the atom also has kinetic energy. The sum of these 2 kinds of energy is the total electronic energy of the atom. This sum expresses the laws of motion that apply to macroscopic particles. To fit the observed behavior of microscopic particles, like electrons and protons, the laws must be modified somewhat. As modified, these laws are called quantum mechanics. The mathematics of quantum mechanics are quite complex, but we don't need to consider the details of the calculations. Our interest is in the results that quantum mechanics gives. This high-speed computer simplifies the task of carrying out the calculations. The equation is punched onto cards and fed into the computer together with instructions on how to solve it. The computer then rapidly solves a problem that is tedious if done by hand. When the calculations are completed, the machine types out the energy values. Let's compare these calculated energies with the experimentally determined energies of the hydrogen atom. Agreement is excellent. Thus we see that quantum mechanics provides an explanation for the specific energies observed for the hydrogen atom. Because quantum mechanics also confirms all other properties of the hydrogen atom that can be measured, we believe the results quantum mechanics gives for those properties that are more difficult to measure. One such property is the location of the electron relative to the nucleus. What can we learn from quantum mechanics about this? To answer this question, we will consider the 1s state, the lowest and most stable energy state of the hydrogen atom. Quantum mechanics gives the results only in terms of probability. A dartboard will help us understand the kind of probability information that we get from quantum mechanics. See where the dart hits. Each throw is completely independent of the others. Observe the pattern of punctures. There are many holes concentrated near the bullseye. Toward the edge of the board, there are fewer punctures. These holes indicate the likelihood that the next throw of the dart will land in a given square centimeter. Where there are many holes, the probability is high. Where there are few holes, the probability is low. These observations allow us to conclude that the probability of the dart landing near the bullseye is much greater than the probability of it landing far away. We shall see that there is a close analogy to the electron distribution in the hydrogen atom. The pattern of holes is centered around the bullseye, just as the electron centers its movement around the nucleus. Compare it to the probability plot for the 1s state of the hydrogen atom, as generated by the computer. What does this plot tell us about the location of the electron? To answer this question, another analogy may be useful: the movements of a hummingbird around his nest. We'll use the hummingbird to represent the electron. His nest represents the nucleus. The nest is located in this small tree in a field of flowers. Let's represent this scene on a chart. Here is his nest in the tree. The hummingbird collects nectar from the flowers here and there around his nest. Let's suppose that we keep a record on this map of the location of each flower the hummingbird visits. Here's one now. We'll mark the location of this flower on the map. Oh, now he's over here. Oops, there he goes. Let's mark it. And now a third. Let's continue plotting these locations. Plotting over a long period of time, a pattern develops. In this pattern, for a given area, the number of pins is much higher near the nest than it is farther away. Again, we have probability information. Thus, we conclude that the probability of the bird landing on a flower near the nest is much greater than the probability of landing on a flower some distance away. We can discuss the average distance of the hummingbird from the nest, but sometimes he will be found closer than this average distance, sometimes farther away. In any event, we see that there are no boundaries to the pattern. Occasionally, the hummingbird lands on a flower a very great distance away. The plot of the hydrogen atom, which the computer drew earlier, has exactly the same meaning. Just as this map tells us the probability of finding the hummingbird a given distance from his nest, so this plot tells us the probability of finding the electron a given distance from the proton. As in our analogs, we see that the probability of finding the electron near the nucleus is much higher than finding it far away. Again, we find that there are no boundaries to this plot, for although the electron is most likely to be found near the nucleus, it occasionally may be found very far away. A limitation of this plot is that it shows probability in only 2 dimensions. We can use animation to add depth to the plot. This probability description of electron location is called the 1s orbital of the hydrogen atom. We note that the orbital has no definite boundaries, although it does have a spherical shape. Thus, the expression 1s is a convenient abbreviation, where the 1 indicates the energy state of the atom, and the s denotes the spherical shape of the orbital. But remember that the orbital represents only the probability of finding the electron at a certain location. If we could observe the electron, at any one instant the electron would be found at some particular location. At another instant, it would be found at some other location. What about the path or trajectory that the electron follows in getting from one location to another? Well, this is a question that quantum mechanics does not answer explicitly. Any trajectory that corresponds to the spatial distribution we see here could be in accord with quantum mechanics. Thus, we can only test trajectory models of the atom by comparing them to the quantum mechanical picture. For example, here is a common model of the electron's trajectory that you have probably seen often. It shows the electron moving around the nucleus in a path similar to that of a planet moving around the sun. We'll call this a satellite model. Let's compare this satellite model to what we have learned from quantum mechanics concerning the hydrogen atom. If the satellite model were correct, the electron would always be at a fixed distance from the nucleus. Then the probability plot would take the form of a circle. The electron would never come very close to the nucleus. But experiments show that the electron does come close to the nucleus, just as calculated with quantum mechanics. Hence, the satellite model is inconsistent with our experimental knowledge of atoms and can be discarded. Although quantum mechanics does not tell us the detailed motion of the electron in the atom, it does tell us the electron position in terms of probability. Far from the nucleus, it is low. Near the nucleus, it's high. We can consider an average radius of the electron position, but there are no boundaries to the atom. The probability becomes zero only at an infinite distance from the nucleus. Since the 1s orbital is three-dimensional, there is a spherical surface at infinity where the probability of finding the electron is zero. Any surface where the probability is zero is called a nodal surface. The 1s orbital has only one nodal surface. You'll recall that the 1s orbital corresponds to the lowest energy level of the hydrogen atom. The 1s level can be further characterized by the energy needed to pull the electron completely away from the proton. For the first level, this energy is found to be minus 313.6 kilocalories per mole. Interpretation of the hydrogen atom spectrum shows that the atom has higher energy levels. For instance, here are the energies of the second and third energy levels. Numerical analysis of energy values shows that these experimental energies are very simply related. For example, the 78.4 kilocalorie energy value may be rewritten this way. 78.4 is just 1/4 of 313.6, and 34.8 is just 1/9 of 313.6. These numbers are most conveniently recognized as 313.6 divided by the square of an integer. Thus, 4 is 2 squared, 9 is 3 squared. The lowest energy is 313.6 divided by 1 squared. We can characterize each energy level by this integer in the denominator. The integers are possible values of the principal quantum number, n, and we can use the integers to label the energy levels. Now let's use the computer to plot the orbital of the second energy level, the 2s orbital. Each point has the same significance as a point on our map, showing where the hummingbird was seen. The pattern of points describes the 2s orbital in probability terms. Let's compare this 2s orbital to the 1s orbital. They are shown here, plotted to the same scale. Note that in the higher energy 2s state, the probability of finding the electron at a larger distance from the nucleus has increased considerably. Though this plot doesn't show it, the 2s orbital, like the 1s orbital, is spherically symmetric in 3 dimensions. Both the 1s orbital and 2s orbital show that the electron is sometimes found a very large distance from the nucleus, again reminding us that the atom has no boundaries. For the 2s orbital, however, we see a new characteristic. There is a definite radius at which the electron is never found. Since the orbital has 3-dimensional symmetry, this radius defines a second spherical surface at which the probability of finding the electron is 0. Such a surface, you'll recall, is called a nodal surface. Thus, whereas the 1s orbital had only one nodal surface at infinity, the 2s orbital has 2 nodal surfaces, one at infinity and one at a specific radius. Quantum mechanics shows that there are other orbitals for hydrogen with the same energy as the 2s orbital. Here the computer is plotting one of these. It is called a 2p orbital. The 2p orbital has about the same average size as the 2s orbital, but note the striking difference in the contours of the 2 orbitals. The 2s orbital is spherically symmetric, but the 2p orbital is definitely oriented along one axis. In this case, the z-axis. Let's use animation to show the other 2 axes, the x and y-axes. The 2p orbital, like the 2s orbital, has 2 nodal surfaces at which the probability of finding the electron is 0. One nodal surface is at infinity, but the second, for the 2p orbital, is in the xy plane. But why isn't the orbital oriented along the y-axis or the x-axis? The answer is that there are 3 independent orbitals of this shape, one oriented along each axis. Each of these 2p orbitals has 2 nodal surfaces, one at infinity, the other a plane through the nucleus. We can now picture our energy level diagram like this. We see that there is only one orbital for the lowest energy level. This orbital, you recall, has only one nodal surface. For the energy level corresponding to n equal 2, there are 4 orbitals, each having 2 nodal surfaces. In fact, for every value of n, there are n squared orbitals, each having n nodal surfaces. We see then that the quantum number n, called the principal quantum number, gives a great deal of information about the hydrogen atom. It indicates the possible energy states and their corresponding energy values of the hydrogen atom. For each energy state, there are n squared orbitals, and each orbital has n nodal surfaces. When we plot still higher energy orbitals, we see that they become more complicated in shape as n increases. But in quantum mechanics, all orbitals are described in probability terms, just as we described the 1s orbital. Our starting point was the experimental energy levels of the hydrogen atom. Because quantum mechanics shows us how to calculate these energies exactly, we investigated it further. The quantum mechanical description of the atom contains only probability information, like the pattern of punctures in the dartboard, and like the map of the flowers visited by the hummingbird. Chemists have found that quantum mechanics also explains many other concepts of chemistry, such as the energy levels of many electron atoms, the formation of molecules, bond energies, and bond lengths. These successes prove the usefulness of the quantum mechanical view of the atom.